Good afternoon. For our for this report, we are going to discuss about state feedback control, and this is Jefferson Ray Arroyo, and I will be your reporter for today. Okay, so let us start with what is state feedback control. S- So, state feedback control is a method in feedback control system theory to place the closed loop poles of a plant in a predetermined location in the S-plane. Placing poles in desired location is desirable because the location of this pole corresponds directly to the eigenvalues of the system. The system must be considered controllable in order to implement this method. This technique is widely used in systems with multiple inputs and multiple outputs as in active suspension system. So um, let us start with so for example, we are given a particular system having a dynamics of x dot of t is equals to ax of t plus bu of t. Y of t is equals to c of cxt plus dut. We know that the open loop system poles are given by eigenvalues of A. Want to use the input u of t to change the dynamic? We will assume the form of linear state feedback with gain vector k. This creates a formula which is u of t is equals to r of t minus k x of t, where k is e r raised to 1 xn. We assume that 1 xn, uh, we assume that 1 that x of t is known exactly, then we have uh, this black diagram as, as a result of the formula. So we have an input of r of t, which is positive, um, and the negative input of k kx, which results to u of t. So we can do is substitute the formula with the two original formulas. So we have x dot of t is equals to axt plus brt b times r of t minus kx of t, which is equals to a minus bk x of t plus br t, while y of t is equals to cx of t plus du of t. So another one, so let us consider the state space model of an SISO system. So with the equation of x times k plus 1 open close parenthesis equals to ax of k plus bu of k, while y of k is equals to cx of k, where k x of k is approximately equal to r of n, r raised to n, with u of k and y of k are scalar. In state space feedback design, the states are feedback to the input side to place the closed poles at desired locations. When we want the states to approach zero starting from any arbitrary initial state, the design problem is known as regulation, where the internal stability of the system with desired transient is achieved. Control input, we have the formula of u of k is equals to negative kx of k. When the output has to track a reference signal, the design problem is known as a tracking problem. So the control input, which is u of k is equals to negative kx of k plus nr of k, where r of k is the reference signal. If we will discuss designing a state feedback control law using the placement technique for regulation problem. So by substituting the law in the system state model, the closed loop system becomes x open parenthesis k plus 1 close parenthesis equals to open parenthesis a minus bk close parenthesis x of k. If k can be designed such that eigenvalues of a minus bk are within the unit cycle, then the problem for regulation will be solved. The control problem can thus be designed as design a state feedback gain matrix K such that the control law given by the equation places poles of the closed loop system with x open parenthesis k plus 1 close parenthesis equals to open parenthesis a minus bk close parenthesis x of k in its desired location. A necessary and sufficient condition for arbitrary poles placement is that the pair a open parenthesis a comma b close parenthesis can be controllable. Since the states are feedback to the input side, we assume that all states are measurable. So let us design K by transforming the state model into controllable conical form. The problem is first solved for the controllable conical form. Let us denote the controllability matrix by UC and consider a transformation matrix T as T is equals to UC W, where W, as you can see here in the slide, as you can see here in the video, is a matrix. It's a matrix which composed of a n minus 1, a n minus 2 until a1 to 1, while the next column is an minus 2, an minus 3 to 1 until 1 to 0, so on and so forth. So the AIs are the coefficient of the character polynomials zi minus a, this is the absolute value, is equals to zn plus a1 zn minus 1 plus until an minus 1 z plus an. So define a new state vector with x is equals to tx. This will transform the system given by the first question into controllable conical forms as x open parenthesis k plus 1, close parenthesis, equals to ax of k plus bu of k. So you can verify it in the equation below. So a bar is equals to t raised to negative 1 at. With matrices having 0, 0 until negative an. The next column would be 1, 0, 0, 0, 0 until negative a and minus 1 until you reach column which is 0, which starts with 0 until it reaches negative a1. And b is equals to t raised to negative 1 b. We first find k such that u of k is equals to negative k x of k. Places poles in the desired locations. Since eigenvalues remains unaffected, under similarity transformation, u of k is equals to negative k t raised to 1 t raised to negative 1 x of k. We'll also place the poles of the original system in desired locations. If poles are placed at z1, z2 until z of n, the desired characteristic equation can be expressed as open parenthesis z minus z1 close parenthesis open parenthesis z minus z2 close parenthesis until you reach z open parenthesis z minus z of n close parenthesis, which is equals to 0. Or you can use the derivative, which is z raised to n plus infinite a1 z raised to n minus 1 until you reach a minus n minus a subscript n minus 1 times z raised to 1 plus a subscript n is equals to 0. Since the pair a bar comma b are the controllable companion form, then we have this result. So a bar minus b of k is equals to a column of 0, 0 until it reaches negative open parenthesis a subscript n minus k1 close parenthesis. So the next column for the equation is 1, 0 until it reaches negative a subscript n minus 1 minus k of 2. You do this matrix until you have a result of a column which starts from 0 until it reaches negative open parenthesis a of 1 minus k subscript n close parenthesis. So please note that the characteristic equation of both original and conical form is expressed as zi minus a absolute is equals to the absolute value of zi minus a prime, which is also equals to zn raised to n plus a1 zn negative 1 so on and so forth until you reach a of n, which is equals to 0. So the characteristic equation of the closed loop system with u is equals to negative k of x is given as um, z of n plus open parenthesis a of 1 plus k subscript n close parenthesis multiplied by z raised to n minus 1 plus a of 2 open parenthesis a of 2 plus k subscript n minus 1 close parenthesis multiplied by z raised to n minus 2 plus until your equation reaches plus open parenthesis a of n plus k1 close parenthesis is equals to 0. So after comparing the two equations before, so we get k subscript n is equals to a1 minus a1 comma k subscript n minus 1 is also equals to a of 2, a subscript 2 minus a subscript 2 until you reach k of 1 is equals to a of n minus a of n. We need to compute the transformation matrix of T to find the actual gain matrix. K is equals to kt minus 1, where k is equals to k1, k2, so on and so forth until you reach k of n. So that is the state feedback control report.